The majority of the test obviously will cover circular motion, but the problems you're noticing on the AP exam have multiple parts, right? And so you're going to have some energy questions and trajectory and all that other stuff kind of tied in, right? Okay. Okay, so it looks like this. You've got a diagram. The diagram looks like this. You've got an angle theta. You've got an object up here, and it asks, what is the velocity of the block at the bottom first? Is that right? Velocity of the block when it reaches the bottom. Okay. Is there friction?
There's no friction.
No friction. So all we have is mg and normal. Since there's no friction, what's probably the straightforward, easiest way to find the velocity at the bottom? Probably energy. Since there's no friction, we would just say that we have a change in height going on. So we have a change in potential. This thing starts from rest, so energy at the top equals energy at the bottom. Right? And energy at the top is gravitational. Energy at the bottom is all kinetic. If we call the bottom height equals 0. And so we've got mgh equals 1/2 mv squared. So the answer should be square root of 2gh.
C.
Which is C.
Not A.
Not A. Alright, so that key is incorrecto. Alrighty. Alright, so 69. Any questions with 69?
What'd you get?
Explain?
He said, yeah.
D.
That's what I got.
Well, I had.
Do you want to explain?
G sin theta.
Alright, so then we're looking for, what are we looking for? The acceleration? We're looking for the acceleration now? Okay.
Sí, señor.
So the acceleration goes like this. In acceleration, what's the probable approach? Will we use energy? I mean, we know the velocity at the bottom. Do we use kinematics or energy to help us find acceleration? Okay, look. In kinematics, what would we need? We know the initial velocity is 0, right? We know the final velocity now. Is that enough information to use kinematics?
I have no idea. Time or distance.
Yeah, we either need to know time or distance, right? Of which we know neither, because they didn't give us either of those things, right? So, or did they?
They didn't give us age. Well, they did give us age, but
Yeah, we could find this distance it travels from here to here using the height h. But the problem is when you look at your answers,
none of them are that weird.
yeah, none of them have an h. Well, there's one with an h in it, right? So it looks suspect. So that doesn't seem to be the way to do it. Okay? We could find it probably using kinematics, but it looks like they're trying to solve it with forces. F equals ma. Now in that case, it's accelerating this way, right? So we want the forces in that direction. So the forces in that direction would just be, mg sine theta, right? Just this portion right here. And there's your theta right here. Theta here, theta here. Okay?
But this one has friction.
Oh, this one does have friction, right? Yeah. So we got to add a new force. That's friction. So now we have minus force friction equals ma. Okay. So A would be, just divide this by m, and there you go. Is that there?
No.
Okay, do we have to do more then?
Yeah.
Plug in
Okay, we got to plug in for this. Okay, so force friction, what kind of friction do we have? Static or kinetic? Kinetic, so we can just do mu force normal. So normal, what's normal?
MG
cosine
Yeah, it's not just mg, it's this part of mg, so that's going to be mu mg cosine theta, right? So that plugs in here, so then I get an mg sine theta minus a mu mg cosine theta over m equals my acceleration. So I just plug this in right there.
But that's
That's not an
option
answer
either.
choice.
That's not an option either, huh?
Yeah,
I
that's
think
what
they
we all
messed it up.
got, but it
Oh,
was like
the
multiple by
bars.
negative and you got it.
Okay, so we're
There's
right
no-
here now, right?
Never mind. They switched the friction thing.
Okay,
Oh, I have.
so that one's not there, huh? You sure?
Yeah.
Yeah.
It's G.
No.
Sine theta minus.
Yeah.
Yeah, this one's wrong. It says G cosine theta minus mu sine theta.
G sine theta minus mu mg cosine theta. Huh.
The closest is D, so that's what we put, but it's not right.
Wow.
Who gave us a defective
But I got D.
physics problem?
I
I
did,
just
because
got D.
I picked D, but D is not
Correct.
correct, is it?
Maybe there's a ratio that
Yeah, maybe there's a trig identity or something.
No, then we'd end up with tangents and all.
and we don't want to use that.
Yeah.
Now, it's not that
Let's take it to
they've given you the proper angle. That's weird. Yep,
They switched.
defective. Okay, it goes like this. An object weighing 4 newtons swings at the end of a string as a simple pendulum. At the bottom of the swing, the tension is 6. So here it is. It's swinging through an arc. It has an mg mass of 4 newtons. It has a tension on it of 6 newtons. All right? What is the magnitude of the centripetal acceleration of the object at the bottom of the swing? Okay? All right, so you want to know the centripetal acceleration. Well, the centripetal acceleration is v squared over r. Unfortunately, we don't have enough information to solve it like that, right? So, let's back up. We also know that the sum of the forces equals ma, right? And so we've got 6 up minus 4 down equals the mass of the object. What's the mass of the object?
0.4.
Yeah, very good, because this is the weight. So weight equals mg. So 4 equals mass times approximately 10. So the mass is around 0.4 for multiple choice purposes times a. So 6 minus 4 is 2 newtons divided by 0.4 kilograms gives you a centripetal acceleration of, I think that's 5, right?
Yeah, 1/2 G.
5 meters per second squared. Now they give their answers in units of g, which is acceleration due to gravity. So that's half of g, right? So our answer is 1/2 g. All right? That's toast. All right, number 6 is E.
Work it.
Work it?
Yeah.
Yeah, angular momentum. We did not talk about this yet, right? This is one of those topics that, for the sake of saving time, we kind of maybe didn't quite get to. So here it is. Here's angular momentum. What's linear momentum? mv, right? Angular momentum is the same thing, except you add a radius to it, okay?
Multiply rate.
And for whatever reason, angular momentum is capital L.
Letters.
Yeah, I think we ran out of letters. So it's mvr, where r is the radius of the object, or the radius of the mass in this case, or the radius at which the mass is operating. So a 2 kilogram object moves in a circle, radius 4 meters at a constant speed of 3 meters per second. Okay, what's the angular momentum of the object? Okay, and they give you the net force, but it doesn't really matter. The mass is 2 kilograms, the velocity is 3 meters per second, and the radius of the circle was 4 meters. So it's 24. And what units? Well, it's kilogram meter squared per second. That's our units. All right? Yeah, that one I wouldn't really expect you to get. Now, there will always be a few of these, because there is seemingly infinite amount of physics for us to possibly study. But we cover as big of it as we can, but there's always something that shows up on the exam that we will not have covered somewhere along the line. Okay? Sometimes the teachers are all in an uproar about it because it's like, well, we didn't know we were supposed to cover that. So anyway, that happens. All right, 66. A person weighing 800 newtons on Earth travels to another planet of twice the mass and twice the radius. The person's weight on the other planet is most nearly. Okay, don't forget how to do this. On a planet, all right, your weight equals gravity. And this is the weight of the person leaving the weight of the planet behind. So G equals big G, mass of the planet over the radius of the planet squared, right? Radius, and this is the mass of the planet, right? And so in this case, we have doubled the mass of the planet and doubled the radius, but the radius is squared, leaving us with 2 over 4, because it's 2 squared, so 1/2 of G. So the answer is an 800 Newton person on Earth would weigh 400 Newtons on that planet.
Because we did that one before.
Oh, we did that exact one before? Yeah, so if they give you some crazy numbers, it's the exact same thing, right? You just redo it. You can do this for the moon if you like. If you do this for the moon, take its ratio of what it is, its mass is to Earth, and the ratio of its radius to Earth's radius, you'll end up over here with approximately 1/6. Okay? If you do Mars, I think it's, I don't know, around 1/4 or 1/5. Okay? Something like that. All right, so what you have is you have this funny looking car with a roll bar, and it's got a mass on the end of a string. Okay, the mass on the end of the string, the mass of the object is 0.1 kilograms, and there you go. So the very first thing is it's sitting still. Draw a free body diagram, okay? Tension, mg, or weight. These must be equal. And then I ask you to calculate the tension of the string. Well, that's pretty straightforward. That's just going to equal mg. So it's approximately, I'm just going to round it to 1 Newton. Okay, it's like 0.98 newtons. Okay?
And would either of those be correct, 0.98 or 1?
Yes, actually either one is correct. Either one is correct. So I'm just going to round it. So that's like 0.98. All right, now, it says it goes through this track. And it goes up, over the top, and then through a loop. Okay? All right, and through the loop part is the part that's going to be the part that we haven't quite covered yet. So we're going to cover that today. All right, so on the way up, it says, first it's right here. So when it's right here, it's accelerating to the right. Okay, and it asks you to draw where the ball is at. And they give you a little dashed line to show you what vertical is, okay? All right, so if it's accelerating to the right, can the free body diagram still look like this?
No.
What has to happen for it to accelerate to the right? There has to be a force this way. And there's only 2 forces that act on it the entire time. Weight, which is always down, and tension. So what has to happen is as the car moves forward, the ball stays still until the string starts to pull it along, right? So it's going to be back here. So there you go. There's your first point on that problem. And then you have to figure out the horizontal and vertical tensions in the string. All right? So here's the deal. Draw a free body diagram. Always. There's tension. There's mg. Now, which way is it accelerating? That way. So that means that we want to set up our coordinate system like this. So what's the vertical tension?
G cosine.
It's mg, right? Which is approximately 1 Newton. Right? So right here, and you've got an angle theta up here, I guess. But I guess it doesn't matter because you just want to know what this horizontal, T horizontal is now, right? And that's giving you the MA of the suspended ball, right? And so the mass is 0.1, and the acceleration, I believe, was 5. So the tension here is going to be 0.5 newtons. Ta-da! So there you go. There's your vertical, and there's your horizontal. All right? Which brings you to going up the hill. And what's the key word?
Constant speed.
Constant speed.
No acceleration.
No acceleration. So if there's no acceleration,
It's just
It's in
force of the
the
weight.
net force is 0. What's the only way for these two forces to cancel?
Tension and weight.
They have to be equal
and up.
and in opposite directions. So this thing's just going to hang straight down, right? And so in this case, the vertical tension must equal mg, so 1 newton. And the horizontal tension must be 0. So there you go. All right, now you're moving down the incline, and as you go down the incline, you're accelerating. Now this is probably the hardest one, because you're going down the incline, and what makes it hard is you're accelerating this way at 5 meters per second squared, but you're accelerating downward at an angle, and the angle they don't give you, do they?
30 degrees.
Oh, they do give you 30 degrees? Excellent, 30 degrees. So this is 30 degrees. Now, the problem is what would we normally do with our coordinate system in this case?
Turn it up.
We would normally tilt the thing, right? And tilt it to make the math simple. But what do they require of us? Yeah, they require our coordinate system to be like this. And so, oh no, for the very first time ever, we had to take this acceleration and split it into pieces. We have to split it into a horizontal and a vertical component. Okay? Now, since this is a 30, 60, 90, and that's the hypotenuse, this is the short side. So this will be 2.5 meters per second squared. Oops, let me make that bigger. 2.5 meters. Let me write it bigger. This is 5 meters per second. This is 30 degrees, and so this is meters per second squared. So this is going to be 2.5 meters per second squared. And this one over here is going to be the short side times the square root of 3, right? So that turns out to be, I got 4.33 meters per second squared. Okay? So, unfortunately, we have to split it up, which gives us this then. The sum of the forces equals MA. First of all, which way will the thing swing? Will it be vertical? It's accelerating this way, right? So that's going to have to swing backwards again. So it's going to have to be back here somewhere, right? Back here somewhere. It doesn't have to be perfect, but just back that way. All right? All right, so in the horizontal direction, our tension on this thing, our free body diagram is going to look like this. We're going to have a tension out this way, and we have mg this way. All right, well, this vertical tension and this one down will combine to give me 2.5 acceleration. This horizontal will give me this one. So let's do the horizontal first, that's the easiest one. In the horizontal direction, I've got only one force, this tension horizontal. And that equals the mass, 0.1, times its acceleration, 4.33. So you end up with 0.433 as your tension in the horizontal. And in the vertical, it's a little harder. Tension vertical. You've got one up and one down. Now let's use our wits about us. Which way do you want to call positive, up or down?
Down.
I want to call down positive because I want to make that positive, right? Just make it easier on myself. So, oops, should be the sum of the forces in the vertical direction equals MA. And I'm going to call down positive. So I've got an mg down minus my t vertical, this part right here, equals 0.1 times 2.5. And we know mg. mg is approximately 1, right? So we can solve for the vertical. And the vertical tension ends up being, what did I get? I got 0.73. Okay?
Or 7.5.
Or, yeah, 0.75 in the, sorry. You're right. In my notes, I used 9.8. And here I'm using 10, so that's 0.75. There we go. Thank you. All right? Now, that brings us to the last one. The last one is it's right here doing a vertical loop. All right?
It's like a weird face.
It does. Like a tongue.
Sticking its tongue out at you.
It's like a big grape.
It's like a big grape.
I like the cartoons
Like a what?
With the mustache.
Yeah, my card is getting smaller as it's going along. It's perspective. It's going away from the teeth. All right, let's talk about vertical circles and vertical motion, and then we'll answer this one, okay? So, if you'll get out your green review packet, we covered all the way through page 5, which brings us to page 6. We just began page 6, but we didn't finish it. Okay? Okay, circular motion in a vertical loop. All right. So we're going to do several different things. Okay? We're going to talk about a ball going around on the end of a string. Okay? Or as last time we had a power strip going around the end of an extension cord.
Hitting the
Right?
end.
All right?
Let's leave that.
So here we go. It goes around like this. Now, if you've got a ball on the end of a string going around and around, first off, is it going to be going the same velocity the whole time around?
Well, it's uniform circular, but it's vertical.
If you can accelerate it correctly.
Will it be going the same speed?
Yes.
I don't know. Maybe.
If you can do that perfect, then if you could just counteract gravity exactly.
Well, if it's the same force making you do it, yes.
Okay. Let me ask you this. If you have a roller coaster with just a track and this thing goes around, will it be going the same speed as it goes around here?
No.
Okay, what's going to be in play? And why won't it keep going the same speed?
Gravity.
Keeps it
Okay, gravity. Where will it be going fastest?
at the bottom.
At the bottom, right? Okay. So let's talk about a roller coaster and talk about the differences first off, okay? So let's say here's my roller coaster car down here, and then it's over here, and then it's up here, and then it's over here. Call that location A, B, C, and D, okay? A, B, C, and D. All right. This roller coaster car was zipping along from over here at a velocity. When it hits here, it's going that same velocity. But it's going to start, at this instant, it starts to change speed, right? No. Well, it does start to change speed here, right? But it also starts to change direction as well, right? At this instant, it's going to start on a curved path, right? And then it'll start to slow down as it goes up. So it's not only curving, but it is also changing speed. So we have two types of acceleration going at the same time. We have that centripetal acceleration, change direction, and we have the tangential acceleration where we're changing speed, right? So we have both. So the questions that they're going to probably ask you will be about this location here and this location here. So let's draw the free body diagram of these two locations first, okay? Yeah, Rudy.
You're just saying that it's changing speed because
Well, you're changing here. Well, you'll see from the free body diagram. So let's draw the free body diagram. What forces act on the roller coaster car here?
Gravity and
Okay. Gravity. In fact, we can draw all of these with gravity right off the bat, right? Because just because we're in a roller coaster car doesn't change the force of gravity. All right, what other forces act on this thing?
normal.
Normal. Now, you got a normal force here. Where's the normal here? To your other right, or to that left. Very nice. Which way is the normal force here? Down. And what about over here?
Down and to the right.
This way.
Take pictures.
Okay, everybody.
Centripetal.
By looking at this diagram, tell me, this one right here, is it changing speed?
Which one?
This one changing speed.
At that
Because
moment?
which way is your velocity?
Is it finishing?
Your velocity's right here,
At
right?
that moment now. Not
It doesn't
now.
matter.
As long as it has no friction.
Your velocity's this way, but the forces are up and down, right? So is there any force in the direction it's going? Is there any force in the opposite direction it's going? So will it be speeding up or slowing down at that instant?
Right there.
No, right at that instant, it's going to be at its maximum speed because that's at the lowest point of the curve. At the top, notice once again, it's going, if we go through the roller coaster like this, the velocity of the object is to the left. The forces are both straight down. These forces are perpendicular to the velocity, so the object will no longer be speeding up or slowing down at that spot. So that's the lowest speed in the roller coaster, because right here on the way up, look what happens. I've got a force in the opposite direction I'm going, so that's slowing it down, right? When I'm over here, notice I've got a portion of my force in the direction I'm going, so it's speeding it up. Does that make sense?
Yeah.
Yeah.
Okay. So you're going to have, if there's a portion of the force in the direction you're going, you're speeding up. If you have a portion of the force opposite the direction you're going, you're slowing down.
Wait.
Yeah, like
If you have a net force in the direction you're going, you're speeding up. If you have a net force opposite to the direction you're going, you're slowing
What
down.
if it's coming this way?
But if you have a force perpendicular to the way you're going, a net force, then what are you going to be doing?
Changing direction.
Okay, everybody catch that?
Turning. Yes.
If I'm going this way and somebody pushes me this way and I have a net force this way, then I'm going to turn. Okay? If I'm going this way and somebody pushes me that way, I speed up. If I'm going this way and somebody pushes me that way, I slow down. If I'm going this way and somebody pushes me that way at an
Break it
angle,
up into components. You
I
turn
speed
and
up.
You speed up.
and I turn. Okay? That make sense? All right. So, this object we know is going to be changing direction. First of all, let's handle this one situation and make sure we understand it. Is at the bottom, if we call this height equals 0, at the bottom we have only kinetic energy. As we go around the loop to the top, what happens to my kinetic energy? And the kinetic energy gets smaller. And it converts into potential energy, right? That doesn't mean it comes to a stop and then it's all potential. That would be a bad roller coaster.
You stop at the top.
All right, so it goes around. So this is conservation of energy as long as we have no friction, right? As long as we have no friction. All right. But now, so I guess my point is please be careful. You're going to have a different velocity here and here and here and here. They're all going to be different. Okay, and you have to calculate them. Okay, so that's different than the other uniform circular motion problems we've had so far. All right? So let's look at this bottom spot right here. The sum of the forces equals ma in the central direction. Okay? Towards the center. All right? Since it's changing direction, I know that I can put down here mv squared over r. But what goes here?
Depends. Going first.
We're talking this spot right here, at location A. What goes here?
What do we define as positive down there?
Good question. Which way do you want to be positive? Towards the center is a good way to pick every time. Okay, because you're going to be accelerating in that direction, right? So that will make that positive, right? And so what goes here?
N minus
mg.
N minus mg. There you go. Okay? Now let's look at the spot at the top. Location C. The sum of the forces equals MAC towards the center. Oops, towards the center. All right, build this for me. What's this going to look like?
N plus mg.
N plus mg equals mv squared over r. Okay, now, looking at that and looking at this, is the weight going to change? No. Now the velocity up here will be less than the velocity here, right? Okay, but where will the normal force be largest then? Will it be up top or down here?
Down there.
Down here for two reasons. Number one is the normal force must overcome gravity, and it has a bigger velocity here, right? Up here, the normal force, gravity helps it, and the velocity is less. Okay? Now, how low can the velocity go?
As low as it wishes to go. Towards negative.
All the way. It could stop.
But look, if I make this 0, can the normal force go to 0?
But it could go negative and say it's holding it up.
It would mean that there would be no weight in the, or that there would be no surface.
No, the surface could be holding it up.
Now, hang on. If we just have an inside loop where the wheels are just on it like a car is on a road, right?
Oh,
It's like
no,
you
it's
drove
not
your
that.
car through a loop.
Then yeah, you're gonna
fall
fall if you do that.
Yeah,
you
because
do
if you
zero.
make this really low, look what happens. Normal force can get smaller and smaller and smaller, right? Until 0. Now, why can normal force just magically get smaller? Remember, it's because normal force is because we have atoms, right? And the atoms are bonded together. And normal force is when you step on the atoms, you smash them together, and they repel, right? Kind of like a spring. But when you don't step on them, they don't apply as big of a force, right? The deal is here is this can easily go to 0, but you can't get rid of mg, right? So what happens is if this gets too small, then that goes to 0, and the thing starts to just fall in free fall. Here's how it works. If you have the ball on the end of a string, what happens is if this ball is going this fast, and if you were to cut the string, it won't go through this circle. What it will do is go through trajectory motion, right? But I want you to visualize this for me. See the arc up top here? That has a larger radius than the radius of my circle, right? So the ball wants to travel this path, but you pull it around into this path. If you slow it down, what happens? The arc of the ball would go like that. So you still have to pull it around, but not as much when you slow it down, right? You slow it down more, all of a sudden you get to this point where the arc up here is the same as the arc of the circle. Does that make sense? At that point, you don't have to pull on the string at that point to keep the ball going in the circle because it's in the same arc as the circle. So what happens if you go slower?
Then it falls.
It will fall out of the circle. Does that make sense? Because it doesn't want to go in the arc of the circle. It wants to go in an arc less than the circle. Does that make sense? So you'll fall out. Now that magical speed occurs. We call that the minimum speed up here. The minimum velocity. This velocity gets smaller and smaller and smaller until the normal force gets to 0. And when the normal force gets to 0, that's as small as you can get on this side. And that's the last point at which you'll still have circular motion. If you go smaller than that velocity, then you're no longer in circular motion. And you're now in parabolic trajectory motion. Okay? And look what happens then. That's 0. So I've got mg equals mv squared over r. So the m's disappear. And here is the magical spot. V minimum squared over r. Or g equals the centripetal acceleration. If your centripetal acceleration is equal to g or less, then you won't go in circular motion. You'll fall out. Now, you know those roller coasters. There are roller coasters designed less than this speed. Here we go. Okay, looking at this spot right here. Okay? Okay, this object right here, it's got a force towards the center, but it's also got a force this way. So it's got two types of acceleration at once, all right? So if we look at point B, we can do sum of the forces equals ma towards the center. And if we do that, what forces do we have towards the center?
Normal.
Just the normal. And that equals mv squared over r. And that would be your normal force at that spot. But we also have this one. So the sum of the forces equals ma perpendicular to that, which in our case is in the y direction. We have an mg equals ma. So at this spot, how quickly is this thing slowing down? With an acceleration of g, right? At that spot. Has an acceleration of g. It has a net force in this direction. So it has an acceleration towards the center and an acceleration downward. Okay? Now, let's talk about this for a minute because I like to make a lot of these circular motion problems into trajectory motion problems. Okay? So let's say that you're flying along this track here and the track breaks right here.
Oh,
Okay?
So you get launched.
So you would launch into a trajectory motion like this, right?
Why couldn't we break it at the top?
Okay, so if we break it at the top, you would launch into a trajectory motion like this, right?
We should
Halfway-
break it
where-
right as
where
they're
it
going
points
straight
down?
down.
What if you break it right here?
Go up,
You'll go
Then
up.
you would go
up and down.
then
up
fall.
and then straight back down. What if you break it right over here?
Go straight down.
Yeah, it shoots you straight into the ground.
Yeah, that's what I was saying.
That's awesome.
What if it breaks right here?
Zero shoot.
It's the Santa Claus sliding off the roof problem, right? You launch down like that. What if you're right over here? Then it's like a,
5-3
Basketball.
yeah, it's one of those basketball shots or whatever, right?
There's
So-
a net at the bottom, a sleep number bed.
Yeah, and there's a sleep number bed right here.
Set to 0.
Set to 0, extra
Just
cushion.
repeat it cloud.
All right, so you have all those different possibilities. While we're talking about this, you remember the one from last week where we had the ball on the end of a string going around a circle like that, right? They call that the conical pendulum one, spinning something like this, or it's the swing ride at Six Flags, right? It swings around like this, okay? So what if you're right here and it breaks?
You're showing that way.
Then you get shot off in a horizontal launch, right? Okay. All right, now, this is what we call an inside loop, where the only place you're really concerned about is at the top, okay? Because if you're not going fast enough at the top, you'll fall out of the loop. Okay, there's another type of ride where it's like a Ferris wheel. If you have a Ferris wheel type ride, like the one at the State Fair, okay, all of these cars are physically attached. And in this case, they don't speed up or slow down once it's operating, right? They're all going the same velocity, right? In that case, at the top, you are obviously going too slow, right?
So you would fall.
You would fall out of this loop, right? You're going below that minimum speed, right? So in this case, there's an mg down, but your normal force or
Pushing
force,
you up.
other force, whatever that is, it's got to be pushing up to keep you from falling in that case. Okay? All right. I encourage you all to go home. I forgot to bring my bucket of water in today.
Go home.
Go home, get a bucket.
See.
No, not right now.
Aw.
Here's your lab for tonight. Go home, get a bucket of water.
And swing it over you.
Yeah, and take the bucket of water and swing it over your head.
You did bring one, the Iceland had flat bucket.
Yeah,
I'm gonna go really slow.
I'm gonna have my bucket.
Tell us to explain.
We can do that with calculators. If you want it to be a little more exciting.
Oh,
See, because these calculators will fall out, right?
you
How
wouldn't
did you
do.
sing it fast?
I wouldn't dare.
You would.
Jump! And then if you go too slow, here. Let's take the expensive part out. No, it's more fun when there's lots of things falling.
In your head.
That's what she said.
That's why I got scars on my head.
I heard that. I heard that.
Yeah, I know.
That was just the buffer going on. I'm playing, Mr. Brody. I love you.
Yeah, whatever. All right,
Fast.
do it fast. Okay, slow.
Slow mo.
They starting to come out.
In the trash can.
All right, now you can do that with water as well, but you notice that when they started to come out, it's going this way. They went into kind of a trajectory motion. They didn't fall straight down, right? Because they already had a velocity, so they fell this way. All right? So they won't fall straight out unless you go. Stop. So there you go. All right. Now let's talk about the opposite of this. Let's talk about an outside loop. Okay? A car going over a hill. Okay, so let's say you're in a car and you're going down a hill and then over the top of a hill over here. Okay, when you're at the very bottom right here, no chance of you falling out of this loop, right? Really? Okay.
Unless gravity was so great.
Okay, you're accelerating this way, right? Now when you're here, you're going to be accelerating downward. Or otherwise you won't stay in that curve. So what are all the forces acting on the object?
Gravitas.
Gravity and normal.
Was almost less than
All right, so everybody, you're accelerating downward though, right? So the sum of the forces equals ma towards the center. So that's going to be mg minus normal equals mv squared over r.
At the very, very top, though, wouldn't it just be equal or wouldn't be accelerating up or down? At the very, very top?
Wouldn't what now?
Wouldn't it have no, at the exact top, it wouldn't be accelerating down, would it?
Yeah, at the very top of the hill, you're accelerating downward.
I was saying you'd be, have, done.
right before when you're accelerating upward then down.
At the top, you're not going to go straight.
Alright, so,
You're going in a path that's curved. Since the path is curved, there must be more force towards the center.
well, if you suddenly cut it off, wouldn't you, like, cut off the rest, you'd just fly straight, except then gravity would pull you down, though, right? Because you got no more normal. But you'd start off straight, though, wouldn't you, horizontal?
Yes, 'tis true. But the normal force is still going to be less than
So
mg.
it's just right before that the normal is equal. Right before you get to the top? When is the normal equal to...
Okay, if your vehicle is changing direction, and if you're going all around like this, then you're constantly changing direction, then the normal force, if we look at the top spot, the normal force up can't equal mg, because if so, then you wouldn't be changing direction. You'd be going straight. Alright?
Like before that the normal force is... Well, then the normal force is...
Okay.
Yeah, I don't know, I'm being stupid, never mind.
No. So like if you're going straight and then you go up like this, okay, normal equals mg, normal equal mg, normal equal mg, but as soon as you start to change
Normal is
direction,
greater than
normal in this case is greater than mg because you're curving up. Okay, the other way, normal equal mg, normal equal mg, but as soon as you start to change direction, normal is less than mg because you're curving down.
Yeah, I was just saying like, their normal is greater than mg as you start to go up, but then as
Yeah.
you start to go back down, normal is less, so at some point in between their normal is equal.
Yeah, that's correct. Somewhere in this path, they'll be equal. That's correct. Along that continuum, yes.
I get it, and then people ask questions, and
Huh?
then they confuse me.
All right, Nia, here's the deal. Is the car changing direction?
Yeah,
Yes. Which way is the center of the path?
downward.
That way. So which way is it accelerating? Downward. So which one's bigger?
That way.
That way is bigger. So mg is bigger than normal.
Yeah.
Got it? You done. All right. Now, here's the trick on this one. What happens when my velocity gets bigger and bigger and bigger? Biggerer and biggerer. Okay. I'm not changing the mass of the car, and I'm going across a radius that's constant. And mass and g don't change, so what's the only thing that can help me get this velocity bigger?
Normal goes down.
The normal has to get smaller. Okay, how small can normal go? To 0. And when this velocity gets to a maximum value, this normal goes all the way to 0. Okay? Now, let me show you why that will occur. If the car is at the top of the hill and stationary, and then the hill would disappear, what would happen? Well, it'll just fall straight down, right? But as you go at this spot and your velocity is to the right, your car wants to go through a trajectory motion like this, right?
As you increase.
And the faster you go, the more the trajectory wants to go out this way. And when you reach the magical spot where the curve of the trajectory is equal to the radius of your curve, this equals 0. Because if you go any faster, what happens is you leave the road. So this is the maximum speed you can go and not leave the road. This turns out to be 0, so these cancel. So, hey, magically, look at this. This is the same thing we had before where it was the minimum speed, right? If you're going around an inside loop where you have a possibility of falling out of the loop, then you have to go at least that speed or greater. But if you're going on an outside loop where you have the possibility of jettisoning off the surface, then that's the maximum speed you can go and not leave the surface. Does it make sense? Let us finish part E of our roller coaster problem. Okay, so here we are in our roller coaster with our car and the string right there. Okay. We're at the top. So what are the possibilities of where that ball could be at?
Hanging straight down.
It could be hanging straight down.
It's going at high enough velocity.
Or
Can we go fast enough that it's like
it could be going fast enough to be up here. Really, we have only those two choices, right? Because at the top, it's not going to be accelerating right or left, because we're at the top of the loop, right? Okay, so how do we find out if we're going fast enough?
yes.
Do Vmax. Some of the forces.
Our centripetal acceleration, the critical condition is when this equals g, right? So v squared over r equals g. Well, does it equal g? Is it greater than or less than or equal? So what's our velocity at the top?
29.
25 meters.
25 squared. What's our radius? 25 meters. So this is going to be 25. That's our centripetal acceleration. And that is definitely greater than g.
So it will not be hanging down.
So will it be hanging down or will it be in the upward position?
Upward.
It'll be upward because we're accelerating it down faster than gravity would accelerate it down. Therefore, the only way to get this thing to accelerate downward faster than 9.8
Slowly.
is to pull it down with the string. So you have to be pulling the thing down with the string. So the free body diagram looks like this. There is tension and there's mg. So at the top, the sum of the forces equals ma towards the center. And so I have tension pulling it down plus mg pulling it down equals mac. And we already know that this AC is 25, so I already calculated it. The mass was 0.1, this was 25. The mass is, or the weight is 1. So the tension will be 2.5 minus 1, or the tension equals 1.5 newtons. All right? Now, I didn't expect really any of you to get that one right, since we hadn't talked about it yet.
Although I have that.
Okay?
I lost by 1 point.
Now, does this make sense? You look at this critical speed, and that tells you whether you have to pull the thing down or whether it's going to naturally fall down. All right?
Because it was a bar and now a roof.
Somebody said that it was just going to be laying on the roof, so I was like, well, if it's in that case, then it's just hanging down because it's a bar.
Yeah, now, some people they thought that it would fall down, and so they put it like right here. But remember, it's just a bar going across. It's not going to sit on the roof. Okay?
Only Mexicans
I
can
was
sit
just
on
seeing that if it was doing that.
Chris, only
All right. Everybody, I want you to turn in your packets to this problem right here.
Oh.
1978. 1978. All right, everybody, let's work this one.
Free body diagram, or do we have to use this thing?
Oh, no, 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 no. Okay. Yes. Now, I always tell you to draw a free body diagram, right? Even if it doesn't ask you to draw a free body diagram, and you're going to need one, draw it anyway, because you can get points for it, even if they don't ask for it. Okay?
Like, right here it says on the following diagram, and there's nothing here, so do we just draw?
Oh, you know what? That may have gotten a typo or whatever. Yeah, so just draw one down there. Sorry, I misunderstood. Okay, there's a couple of things on here. The mass of this device is 0.5 kilograms, okay? 0.5 kilograms. All right, here we go. Let's make sure we finish this up before we have to go.
Let's start with C.
Okay, A. It asks you to draw the free body diagram, okay? So we've only got a string attached to it, so there's tension, and there's gravity, so there's mg. So there you go. All right, so there's A. Part B, it asks for the speed at point P, all right?
T plus mg.
It tells you the tension in the string. The tension in the string right here is 20 newtons, right? So at the top, if we just look at this, we don't know a whole lot in order to find the velocity, but we do know that F equals ma, and it is going in a circle. And so towards the center, we have tension plus mg, and that equals mv squared over r. So we can maybe find the velocity that way. So they give us that the tension is 20 newtons. They give us the mass of 0.5. They tell us to use g of 10. This was back before they allowed you to use a calculator, or they didn't have calculators.
Right.
Right?
78.
78.
A TI2.
Actually, you know what? 78. That's right back when the liquid crystal calculators first came out. That made them efficient enough for everybody to buy it. Probably about when I got my first calculator.
78?
78. 79. Actually, it's probably 79 or 80 when I got my first one.
I don't know, it's not.
Okay, the mass is 0.5, velocity squared over a radius of 2 meters. So the velocity is 10 meters per second.
Yay.
All right, now, next question is, what's the increase in kinetic energy? Okay, as this moves from P to Q, how does it get kinetic energy? Where does it come from?
The potential.
All right, so from here to here, the potential energy is converting into kinetic. So we just need to figure out how much potential energy is turned into kinetic. Well, our change in potential energy is going to be mgh, delta H. That's 0.5 times 10 times a change in height of 4 meters. So that's, what, 20 joules. So you increase 20 joules of energy in kinetic. So that's our answer to part C. So part D is, what's the tension? All right, free body diagram. Tension is up
Greater than gravity.
and mg is down. Yes, and I really should draw that bigger than gravity because it's going to be accelerating up. So the sum of the forces equals ma towards the center. So tension is towards the center, gravity is opposite. And that equals mv squared over r. But this v is which v?
The increased V.
The
Plus
increased
20
v at the
joules.
bottom.
So the plus 20 joules.
All right, so I need to find the velocity at the bottom. So
20 joules equals 1/2
1/2 That's where?
Okay, but wait a minute.
Kinetic.
Whoa, whoa, whoa.
20
Energy at
plus
the
the
top equals energy at the bottom.
Yeah, so
The energy at the top is,
kinetic and potential.
it's kinetic plus potential, right? And at the bottom, it's
Just kinetic.
kinetic, because we're assuming our 0 point to be right here, right? Okay, we know that this increase in kinetic is 20 joules right here, right?
Yes.
But we can't forget the original kinetic we had.
What happened to be squared?
1/2, 0.5, and our original velocity was 10
So 100.
squared, so that's
100.
25 plus 20 joules gives us 1/2 mv squared. M is 0.5, so 45, and that's 1/4.
That's 4.
So multiply that by 4, gives you v squared,
So it's 180.
180. So the square root of 180.
But you don't have to, you can just plug it into the 180 because you need the square root.
Oh, right. So v squared is 180. Very nice. Meters squared per second squared. So we can take that and plug it in here.
Yep.
When we plug in all of our numbers now,
Tension is 50.
since we're running out of time, the tension is 50 newtons. Very nice.
Mr. Bailey, I just forgot to do them.
Can you what? Yes.
I thought you said that
All right.
early.
I am going to post the key out on the wall. We have a test next time. So come prepared. I want you to do good.